The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to our Design Time Costing webinar. I'm Erin, and I'm just doing a very quick introduction today for Craig Spears, one of our senior software engineers who's going to be doing the webinar. So today we're here to talk about design time costing, which, to be honest, it's a very fancy marketing term for a whole bunch of very specialized functions that our software does around earthwork quantities and costs. And specifically, it's costing as you design. So Craig is going to be going into quite a bit of detail around earthwork quantities and costs and working with them. And we have a bit of a surprise for the attendees on the line today. We are actually going to be doing this in RoadEng version 8, which is coming out to beta here shortly and releasing this October. So for those of you on the line, it's a sneak preview before the official sneak preview that we have scheduled in our calendar. Yeah, so with that, just a couple of pieces of housekeeping. Of course, you are muted per normal on our webinar series, but feel free to ask us questions through the GoToWebinar panel. We will be checking them throughout the broadcast. And this webinar is being recorded, and it will be available as a private link through our YouTube page. As I said, this is a sneak preview to version 8 before our official sneak preview in September. So we will be making it as a private video and sending the link out exclusively to the folks on this webinar and the attendees that registered and weren't able to attend. So with my couple quick disclaimers and the fact that I wanted to, again, echo this is beta software, pretty stable beta software, but you never know. With that, I'm going to pass it over to Craig, and he's going to talk to you a little bit about design time costing.
Thanks, Erin. Good morning or good afternoon, everyone. Start showing my screen here. Yeah, so I'm going to talk today about, as Erin mentioned, earthwork costing. Some of the things I'm going to discuss are kind of textbook stuff that I'm sure many of you are aware. Some of the other things are somewhat novel, and they've come from our optimization technology, so I'll be showing you some of those things. And as Erin mentioned, this is going to be done in beta software, so hopefully all will go well. For us, this is a great opportunity to test our software, and it also gives you guys a bit of a look at it before it's released. So having said that, I would say most of the tools that I'm going to show you are actually available in our standard version of RoadEng. They will be available in the standard version of RoadEng, with the exception of the optimization, which I'm going to run an optimization at the end. That is not part of our off-the-shelf RoadEng product. It's a separate product. So what I've got. What I've chosen as an example here is it was an example we got from a university. I believe it's real. It's a real road realignment, and it's a county road. It's not a super high-end road, and it's not a super low-end road. It's a public road. It's about 1.5 kilometers long, and what I'm going to go through is some techniques that people would go through to design the profile in a road like this and balance the earthwork. Before I get into that, I just talk very briefly about volumes and cross sections. So here is a typical cross section. The dark line here on the top is the ground line. This line here, we've introduced a rock surface that is a couple of meters below the ground, and the red line here represents the subgrade line, and I can show you the areas that are tracked underneath the subgrade, and these are areas that we are principally interested in when we do the vertical alignment. You can see also there's layers above subgrade, various engineered materials that are being placed above the subgrade line. These are expensive materials, obviously, and you'll want to track them. Particularly if you're changing the length of the road. but in terms of vertical alignment, positioning, they don't have a lot of significance. They are often ignored when considering vertical alignment position. But again, they represent a very big cost, and they should be tracked. In the procedure that I'm going to follow, those materials, by the way, could be incorporated. We could map them into our mass haul volumes, and then they would be tracked. But I haven't done that. It's not really normal to do that. So as in just about any kind of software or manual calculation, volumes are derived by what's called the equal end area method. So you saw me shade in a fill volume here. Let's shade that in again. So there's what we call subgrade fill volume, and it's a material type overburden. So that volume is calculated on a cross section here, and what happens is an adjacent section volumes are calculated. Sorry, an adjacent section areas are calculated. Just zoom in a bit here. So I'm looking at a section here. I've got a similar section here with different volumes, and to get different areas. To get a volume from those cross-sectional areas, I take those areas and multiply them by half the distance to the next station. And that's pretty standard textbook approach. And obviously, if you increase the number of sections, the accuracy of your volumes increases, and it's virtually becomes as accurate as you want. In other parts of RoadEng, there is ways to calculate volumes between surfaces. That's done in our terrain program, but here in location, we do what's called the equal end area calculation that I just described. So one of the first things to look at, and again, this is really textbook stuff, is what we call expansion and compaction factors. And they can be confusing. They're very simple, but they can be confusing. And here's where you set them. So for each different type of material, you have a cut factor and a fill factor. In our software, those factors are simply multipliers. And if you want to report volumes in bank cubic meters, which is very typical, you will always have a cut factor of 1. That's the material volume that's in the ground. What normally happens for a material like overburden or a softer material is that when it's dug out of the ground, it's expanded, it expands. And then when it's placed back into the roadbed, it actually compacts from its original state. So the effect of that is a fill factor that is greater than 1 for a soft material. For a hard material like solid rock, you have the converse. You have the in situ cut factor is going to be 1, and the fill this time is actually the material becomes bigger. You cannot compact it less than it was originally in the ground. So you typically get a fill factor that's less than 1 for materials like solid rock. And these factors are important. They can have a significant effect on your costing and on your quantities. So I pay special attention to trying to get these as close as you can. I mean, it's not a exact science, but it's well worth spending the time to try and get these factors close. The other things that come with material that are sort of similar are cut and fill angles. That's probably the subject of another webinar, but they are quite important. You see in solid rock that I'm able to cut at quite a steep angle and so on. So that is really the source of information that goes into the into the earthwork calculations. Again, I'm sure everyone is familiar with that. It's kind of a refresher. So the next thing I wanted to show you is maybe not quite so textbook, but it is textbook, and that is a concept of cost for excavating and embanking and moving materials, and that's something that we've worked on and built it into our software so that for each of those materials you actually have an excavation cost and you've got an embankment cost. And based on many conversations I've had with design engineers, these costs aren't typically well known at the design stage. And I think in future they will be with this concept that I'm talking about of actually watching your costs while you're designing it, what we call design time costing. Obviously, these costs come into play when a road is put out to bid for construction. The construction people know what these numbers are. They've got ways of calculating different things. But at this stage here, I would say it's good to have some costs that are representative. They don't have to be exact, but it's good to have them. Then you can compare two different alignments to see how they compare against each other in terms of costs. Just for note, the solid rock cost is quite expensive, dollars per cubic meter, and that would represent blasting of rock. So those costs, basic cut fill costs. The other costs that are important in earthwork are the movement costs, and they're again probably not as well or as commonly used by designers as other things, and they are broken up into three categories, or up to three categories. So in this case, we've only got two. We've got a freehaul cost, which is less than 150 meters, and we've got an overhaul cost, which is greater than 150 meters. So along this axis is distance of the material is moved, and along this axis is the dollars. What you see in this graph is that for freehaul, there is virtually no cost to move dirt a very, very short distance. There's no loading cost. Whereas with overhaul, it costs you the loading cost before you move anything even a meter. You incur a loading cost to pick that material up and load it. So when you look at this graph, which presents the economics of hauling, this line, haul line, and it would carry on up, and this line here is your overhaul line, which if you ran it across, it would intersect the axis over here, and that would be your loading cost. So clearly, you shouldn't be overhauling in this area here. It only makes sense to do it beyond this point, and that's kind of what this graph is telling you. Right now, you have to fiddle with these numbers a bit if you know your freehaul and overhaul distances, but it's not difficult. In future, I think this dialog box can be made to be a bit more responsive in terms of being able to just enter a freehaul cost or freehaul distance or overhaul distance. So those costs are going to tell you how much you could expect to pay for moving material around, and the combination of these two costs gives you a total cost for your road design.
And what Craig, I'm just going to pause you for a brief second. We did have a question relating to that dialog box, so perhaps you'd like to go back into it for just a split second.
Sure.
So the question we received, is it possible to adjust the distance, in brackets 150 meters, of the freehaul to force it to begin loading at 80 meters or some other set distance?
Yes, it is. And what I said quite very poorly is that it's awkward to change just the distance distance. You can change the distance by changing these factors. So if you make your loading costs less here, I would expect, if I bring this down to 0.3, update this, you see that my freehaul distance is now 75 meters. So the short answer is yes, you can, but you have to do a bit of trial and error to get those distances. And I know those distances may come from machine productivity, equipment productivity charts and so on. You can get them in here. It just requires, at this stage, a little bit of fiddling. It's not hard. I could zero in on 80 pretty quickly by fiddling with the costs here. Does that answer your question?
Yes,
I will assume that
great.
Yes. Okay, thanks. And good question, by the way. Great question. And yeah, I've heard that many times before. People understand those distances. They don't so much know about the costs. And in this model, we want some costs. We want to know a ballpark what the costs are going to be. So as I was saying, with these costs, we get for any given alignment or any given design, which includes changes to the cross section, different vertical, horizontal alignments, we get a cost calculated. And it's kind of cool because if you make a change here to your alignment, just move something here a bit, watch over on my right side, that cost should update. There you go. So I've added a few $1,000 by moving that IP ever so slightly. So similarly, if I move the horizontal alignment, you're going to see some costs. So right away, you can get a comparison between different things. It's easy. There's not a lot of work involved for you to set this up or copy stuff into spreadsheets and calculate centroids or do any of that kind of stuff. You have it all here. You just make your change and have a look. And of course, as you go, you may want to refine the costs that you use. It just keeps getting better. So let me change my mass haul. Let me go through with you what would be I guess a more conventional or a conventional way, it still is conventional, a way to design the vertical alignment. So what I've got here, I've got the profile, and below it I've got a mass haul graph, and again this is pretty much textbook stuff, but the mass haul graph, if it's dropping downwards, it means you're filling. So where you can see it here, we're filling all along this section. And then as it starts to rise up, we are cutting, and then it fills a little bit, we're cutting. So this is, the mass haul graph is an accumulation of material moved. And the horizontal axis is station, and the vertical axis is volume. So it's a very useful tool for visualizing what, how much material has been moved, how balanced the road is, things like that. You get a very quick overall feedback, and people who use it really appreciate how powerful it is. And it's been around forever. It's been around in more than 20 years that I've been involved in road design stuff, and it's a great tool. And I have to say that there are a fair number of people that don't really understand how it works. My recommendation is to work on it because it really is a handy visualization. Where the mass haul crosses the zero line is what's called a balance point. So if you were to stop construction here, you wouldn't have any excess material. So yeah, those balance points are places where your cut and fill are balanced. Now in this particular design, you can see that I'm cutting all the way up this hill here, and by the end of this alignment, I've got a surplus of material. I've got, that's it, it's showing me at the end of the alignment, I've got about 6,000 cubes of extra material. left over. And as a designer, you need to know what's going to happen to that material. It can't just vanish. Maybe you could waste it somewhere along the way, or maybe you're going to have to change the alignment. Maybe you need to haul it off to a pit. So you have all sorts of options, but I think you have to figure out where that material is going to go and how you're going to get the design balanced. So let's just try a couple of things. Obvious thing to do, we've got a hill coming up here. Let's just say we have a pit location in here somewhere. So I'm going to add a pit. I'm just going to get rid of some material by hauling it away to a pit. So I'm going to say at station 1400, I'm going to create a pit. And now we're actually into, by the way, some of the new costing tools that come out of our optimization technology. So I've added a pit at 1400, and let's say it's 3 kilometers away, 3,000 meters, and it will accept any material. It's a waste pit. I can throw anything in there. And it costs me, let's just say, for instance, $20,000 to maybe fix up the access to it or open it up, do something to actually activate that pit. And I'll come back to why that's important in a minute, but here's a pit option we have. Let's just add that and see what the effect of this is. So I'm going to recost the alignment. What I expect to see is this. Yes, right here at 1400 is gone off to the pit, and it's dropped the mass haul down. And again, it's still cutting on the way up the hill, but it ends up at the end of the alignment, so we're balanced. So we've effectively taken material and hauled it 3 kilometers down the road, dumped it, and this is our mass haul. And the cost has changed. The cost now accounts for getting and moving that material out to the waste pit, which is interesting. So, yeah, there's one option right there. What if I put another pit in here? Maybe I have a couple locations that I could spoil to. What if I put one down here? And I know that this one's, let's say it's cheaper. So let's go down and add another pit at the end of the road. And I'll say it's the end of the alignment. And this one, the distance, I'll say it's pretty much on the alignment. I only got to go 50 meters away to dump my stuff. And this one's cheaper to open up. It only cost me a few $1,000 to open that one up. Let's add that one, recalculate, and see what is economic. And what this tells me is it's way cheaper just to move that material to this pit location. So what you have is a tool that can help you decide on where to spoil material to, or where to draw material from. And without getting into too many mind-boggling things, you can actually control the material types. So you have a concept of quality of material. So for instance, if I was borrowing material, if I had a borrow pit, I could tell it what type of material is coming from that pit. And on my alignment, I could also say that I only want to fill with certain qualities of material. So you know, these kind of more complicated problems start to boggle your mind when you're doing this manually, and this tool will help you. It will tell you how to move materials around economically, considering the qualities of the material. How are we doing for time here? I'm going to keep going, I guess. I don't have too much more to go here. Okay, so let me just remove these pits. Look at another way of doing things. Okay, so we're back to the unbalanced alignment. Another way of fixing this problem is to change the alignment, of course. So suppose we got too much material, we could actually move the alignment. We could pick the alignment up here. We could pick it up and get rid of some cut material by moving the alignment. Let's suppose I pick this up a little bit here. Let's try and manually balance this alignment as quickly as we can. Gone a bit too far, zoom in. Anyone who's designed roads probably done this. You can get quite good at it. In fact, almost intuitive, I imagine. You can see things very quickly. By the way, we're almost balanced now. 500 cubic meters. Which way do I want to go? I want to come down a bit, I think. Oh, too far. You get the idea. Don't make me suffer. Let's pretend that this is balanced. It doesn't have a whole lot of material left over. So we balanced the road. Great. Now we're feeling pretty good about it. Let's have a look at how material is moving here. Here's our mass haul graph. We have a new graphic which shows the way material is going to be moving. We call this the opti-haul graph. It's down at the bottom here. Let me just, whoops, maximize.
And Craig, we do have an additional question. So I'll just
okay.
So is there any way to allow for unsuitable material?
Yes. Yes, absolutely. The unsuitable material is covered by what I just talked about with quality. So you can assign certain qualities to your alignment. So I go here, assign parameters by range, and I go to fill types, and I really don't have any special constraints on quality, but I could say I want quality 4 or better. I have materials and they're all ranked by qualities. Some of the qualities are unsuitable. Quality 1, quality 2 would be unsuitable. So by setting the right qualities, you can make material unsuitable. And that was a good question, by the way. So this graph that I've got at the bottom is really showing me how the material is going to be moved in the most economic way it can. And you can see that because I've moved the alignment up, we've got traveling. It's in the category of overhaul. This band here is free haul, so we've got a bit of free hauling. So when you're designing your alignment, you're trying to move everything into the category of free haul. Obviously, you're trying to keep your grades and your K values within your standards. It's a tricky problem to do manually. I'm sure people who've been doing it for years have a good intuition about it, but for those who haven't spent years and years doing this stuff, it's a tricky problem to get the best alignment out. And we're trying to build tools that will help that process. So at the bottom here, just showing you what's going on, I've got material moving backwards up this hill. My mouse is misbehaving. So I've got material you can see down there moving up this hill. Let's suppose I don't want to do that. That's not something that's constructible. I can control my movement. I can go in here and say, look, I want to move forward. I want to move forward from, let's say, 0 to 400. So I'm going to put a direction constraint on the movement. Just going to go ahead and do that. And then I'm going to recost, which causes the recalculation of all the movements. And now you can see that no longer is the material moving uphill. We've got this material moving forwards. And of course, because we've constrained it, it's a more expensive. So again, you've got another tool that will let you play with things, try things, finding a good design that's safe and all those other things, and that is economic as well, and is constructible. So that that's really all that I wanted to talk to you about design costing. I thought maybe just as a final piece on this seminar, I would do an optimization for you. I don't know if you've seen our other seminars, but let me take this constraint off. Put it back on here. While I'm doing this, maybe some questions, if there are any, it'd be a good time. Recalculate the recost. Okay, so we got an alignment, and it's pretty much balanced. We think it's pretty good, and it costs $574,000. Let's optimize it just for fun. So I'm going to use the same curve locations that I created there, which makes life easier for the optimizer. So I got this user-defined option, and I'm just going to go ahead and push the optimize button. See what we get. Takes a second. As I mentioned, this is about a 1.5 kilometer road. It's not huge. Large problems can take a little while, but you're getting a mathematical solution that it guarantees certain things. It guarantees optimality under certain conditions, and it's very useful as a guideline, if nothing else, to see what is the lowest cost solution. By the way, I didn't make this profile up. It was given to me. That's not entirely true. I did tweak it a bit, but it was essentially given to me. So there's the optimized alignment. Right away, you can see a huge cost savings. The two alignments look very similar. Sections of one, we're doing more filling. Sections, we're doing more cutting, but you got a very, very similar alignment, but it's almost about half the price. Very typical. Let's set this current and have a quick look at the mass haul graph. So this new interface is a bit new to me. So set current, and there we go. There's the profile, and you can see visually right away that this mass haul graph is oscillating around the zero line a little tighter, and that there's more movement in the category of free haul, and there's less cutting and filling. If you compare these two, you can compare them side by side, you'll see that there's reductions in cut costs and fill costs and haul costs. So you get all these reductions, and that alignment you can now go and have your way with. You can modify it whatever you want, but you know you have a guideline. And that is everything I've got, Erin. Is there any final comments?
Excellent. Well, thank you, Craig. We'll give it another minute or two to see if there's any other questions lingering from our audience. If not, feel free to contact us after the presentation. You're welcome to do so. You can get us at sales or support at Softree.com. So that's sales at Softree.com or support at Softree.com. Both those are our general mailboxes. And as well as mentioned, this video is going to be made privately available for you. We'll send it out to yourselves as well as the folks that weren't able to attend that registered, as this is a sneak preview for version 8 featuring our new interface. So I don't see any extra questions. So with that, have a wonderful rest of your day, everyone. Thanks for coming.
Thank you, everyone.